start. So this topic might look quite verbose, but actually what we are trying to do in this, we are trying to create a very proficient in terms of cost as well as in terms of efficiency. We are trying to create a data pipeline by just using open source technologies. A quick background about me. I currently work as a senior data engineer at Bureau.id. Earlier, I was also working at Karma Life. I joined there as a founding data engineer, and then started leading the team, became data lead, data team lead, and so on. So at my regular day-to-day job, I do data engineering, MLOps, LLM things newly started, so all those things. I also regularly share my insights on LinkedIn as well as on Medium. So this is a QR code you can scan and connect with me on LinkedIn. Right. So the topics we'll be covering here is like Kafka, Parquet. So this can be better told as encoding. Then Metaflow and Superset. So the logic behind the talk is, I just want, like, let's have a first raise of hand. How many of you have heard about all the 4 things? Okay, at least 3 of the 4 things. Okay, cool. So we have a mix of people here, right? So even if you are aware about this particular tools, right, what I'll make sure that you understand the design principle behind that, so that you can take a call whether you want to use it in your particular use case or you do not want to use it in your particular use case, right? So the design philosophy of the talk will be, we'll start with data ingestion pipeline, which is Kafka, right? And then we'll think on what format of data should we be moving through Kafka, what format of data should we be storing at our like whatever cloud that you use, either AWS, Google Cloud, whatever. So what format of data that we should be storing at our cloud storage for more efficient analytical workloads. And then we'll also cover the 2 use cases that we can use with that data, building MLOps pipeline using Metaflow, and also analyzing the data sets through Superset, right? What's the design principle behind the Superset? Cool. So we'll start with Kafka. General introduction, many people are already aware about what's Kafka. So Kafka is a streaming tool, a streaming platform, right? What streams through it? Events stream through it. What are the events? Events are the immutable object, right? Which contains an information that something has happened at a particular event of time, like something like that, right? So event streams through the Kafka, which is streaming platforms, and basically it's also very highly scalable and very high throughput. So the requirement of high scalable and high throughput basically comes from a design principle that I'll talk in the next slides, and why it was built, right? So the origin of Kafka basically happened in LinkedIn, right? What happened in LinkedIn? They wanted to move the data. So earlier LinkedIn was only working with transaction OLTP databases. Then later on they realized that the actual worth of data is once you analyze the user behavior. So they wanted to move their transactional load to, let's say, Hadoop, warehouses, like those things. Now the problem arises there is that they have multiple data sources, right? And the scale of data which LinkedIn operates on is huge, right? So there's one problem with they have multiple data sources. They have to connect a data source to a data destination. That's one problem that they were solving. The second problem that they were solving is they were trying to send data as a log. Now don't confuse log here as like your application log. It's not your application log. Log is basically an append only structure where you append whatever the latest data that you receive at the end, right? So that's basically what log is, right? So both of these use cases they wanted to solve. So if you see, right, they have lot of data sources sitting in Oracle and different data sources. Now they wanted to move this data into Hadoop and data warehouses. If you think that they could have built a customized pipeline to maybe move Oracle to data warehouse and then again for reverse ETL some other pipeline, it would have resulted in big of n square problem, right? So they wanted a very scalable, efficient data pipeline that they can build over this data structure for movement of data at a very high speed because they mostly work on real-time analytics. So a very high level overview. Kafka consists of producer which produces messages to the topics. Topics are basically divided into partitions, and then there are consumer groups which consist of consumers which consumes the data from the Kafka. So now we will go and deep dive into each component of Kafka to understand the design principles. So we'll start with producers. So we'll first discuss the structure of producer, and then we'll discuss what's optimization that we can do at producer to make our data load more efficient. So it started producer record, right? And it has 5 keys: topic, partition, key, value. First thing that happens with the partition is optional. It's not always mandatory, and I also do not encourage you to use partition always, right? Because otherwise you'll become very choosy. So instead of that, you have key and value. You do the serialization. There are different types of serialization that you can do with the data. and then you do partition over it to put the data message into a particular partition of the broker. I'll discuss partition and broker also in the coming slides so that you get more context, but let's stay at the producer side. So once the data gets recorded at the partition, the broker says, yes, I have recorded the data, I have written that to the disk, go ahead with the next record production, then it's success, then again producer starts. If it fails, a retry happens. Right, now coming to broker, right? So what broker is basically, so broker basically gets the messages from producer, stores that, assign an offset, and also like acknowledges the producer that, okay, yeah, I have consumed that message, I have written the data in the disk. Now go ahead with the next message, right? Also, there is also one point in broker is, there is also a zookeeper that they use for coordination and other things. So what they do is, they also select a cluster controller. The broker, one of the broker become a cluster controller. The job of that cluster controller is, that the cluster controller is responsible for defining a leader and the replica of the partition. So if you understand the Kafka structure, right, it's very high fault tolerant. It's highly available. How do they achieve that? They achieve by taking a partition and replicating it across different brokers. Your different brokers can sit into different regions, right? So that's how they. So, but they always have one leader and one replica, like or you can like change that as well, right? So to have your fault tolerant systems. So that's how they do that. But all the reads and the writes will always happen through the leader. Again, like simple consumer stuffs. The only thing that you should take from this slide is, each consumer can consume multiple partition, but each partition can only be consumed by one consumer. You cannot have like one partition getting consumed by multiple consumer. The reason behind that is, otherwise you will have duplication of the same message getting processed. Right. So till now we have discussed few stuffs about what's Kafka, why it was built, dived into different components of it. Now we will move to the partition. Like once you move to the Kafka to production, right, the first question that comes from your product management team is, how many partitions that you want this Kafka to have, right? So if we should always, in the distributed system, we should always start with an end goal in mind. So let's say our end goal is that we want to achieve a throughput of, let's say, 1 GB per second. Right? With that 1 GB per second, you should like then join the dots from backward. So let's say 1 GB per second, your partition can only have a throughput of 100 MB per second, right? So with that, you will need to consume 1 GB per second, 10 partitions. Now each partition can only be consumed by one consumer, so we'll have 10 partition and 10 consumers, right? But now if you have 10 partition and 10 consumer, your workload is very efficient, like it's working fine on its optimal stage. Now here one key factor is, we are assuming that the distribution of the data is uniform. The data is not like skewed distribution at one partition. That I'll also explain in the coming slide what happens with that. But with this slide, let's assume that the data is uniformly distributed, right? So now if you have 10 partition, it's okay, everything is working fine. But the place where you start having like lesser partition, 5 partition or things like that, your producer will be blocked. They will be keeping the data in their buffer memory, waiting for the data that has already been pushed to get cleared, and then they will push the data. Your consumer will get delayed, and things like that will start happening, right? So it always decide the partition first, depending upon the end goal in the mind, right? So now we'll discuss on the partitioning strategy. So now in the previous slide, what we have discussed is that the distribution is always uniform, that each partition has a uniform amount of data. But that's not how the real world works, right? You always screw up things. So what happens, how can you screw up things? There's a default partitioner, right? That's what's responsible for moving your messages to the partition, right? Now there are 3 ways a default partitioner works. The first way, it's like you provide a partition to each message that you produce. That's a very choosy way, don't do that. The second way, you can provide a key, right, to the default partitioner. Depending upon the key, it will like calculate the hash of the key, then modulo of the number of partition available, and then assign that to the partitioner. If you do not provide key, if you do not provide hash or partition, what will happen is your sticky partitioning will come into place. How sticky partitioning works basically is that they have 2 parameters, linger MS and batch size. So linger MS is the amount of time it will wait for the batch to get collected to transfer, or either the batch size of that much data has been collected to transfer. So either of these 3 will happen, and your data will get assigned to a proper partition, right? Now we'll discuss how the skewness can come into this picture. So let's take an example, how the data skewness can come into this picture. So let's say you are owning a cheese factory. Now you want to record all the purchases that are happening on the cheese factory with the help of Kafka's ecosystem. Like you want to set a Kafka for that, to recording all the cheese factory thing, right? Now you came up with a logic that let's use the key user ID. No, but you have forgot on this use case that let's say if you have use a user ID as a key, there will be some users who are consuming, who want your cheese every day, maybe every hour. You make so good cheese, so they want the cheese every day or every hour. But then there are some users like who do not like cheese, right? Who might, or who like cheese moderately. So they might order once a month or things like that. Right? So if you use user ID as the key, what will happen is that your certain partition will be filled with lot amount of data, and the other partition will be filled with less amount of data. So that what will happen with the skewness of the data, right? What happens when the data gets skewed in the partition? Everything gets impacted, starting from producer, broker, and consumer. How they do get updated? Your producer is still waiting with the data in their buffer memory to waiting for the data to get cleared so that they can put the new loads. How the most impacted part in this thing is your consumer. How your consumer get impacted? Your consumer get impacted because the consumer are designed to obtain a load at a certain throughput. Now you have provided a huge amount of load for that, because one partition can only be consumed by one consumer, right? So now that consumer has to vertical scale to match that data load, but that's not possible, right? That's a temporary solution that you can do for some time, but till how much memory you will scale that? So then what you can do is, instead of that, is design a good key. What do I mean by good key? You should use a key which has more granularity in it, right? More granularity in it, and also make sense when the ordering of events happen. More granularity, by that what I mean is, let's say instead of user ID, you would have chosen purchase ID. Now when you use purchase ID, what happens is, it is more granular than user ID. And also, like the events that happen in a purchase, right? Let's say adding to cart, going to payment page, doing the transaction. Those ordering makes sense. As you know that Kafka maintains order only through the partitions, right? So that basically the purchase ID things basically make sense here. So you start with a good key, which has more granularity and things like that. The reason behind that is increasing partition in Kafka is a very tough problem. So it's like you can say you can increase, but you should not, right? So it's always to design these things first with an end goal in mind, so that you do not end up in certain situations where you have to do some hacking to make your needs go through. Cool. So now we have discussed about Kafka. We have discussed about the design principles, why that was built on LinkedIn, what problem did it solve. We deep dive into each components of Kafka. We also understood the partition and partition assignment. Right? The next thing that you should be worried about, not worried about, but basically this is what the design principle in Kafka, which makes Kafka much more performant than any other messaging queues, if you consider Kafka as a messaging queue. So what are those things, right? So first thing is Kafka do sequential reading, right? So the sequential reading is always faster than the random access, we all know, because on the SSDs, right? If you do sequential reading, the difference would be like KB to MB comparison. The Kafka do not have their own caching system. They use operating system cache system, right? So they do not have to double buffer the data once to put into the data and then buffer it to update the cache system. It gets updated automatically, and it's very fast as well. The third thing that Kafka boasts about is its stateless broker. So it do not maintain the state of till what that I have consumed for a particular consumer. It do not maintain that state. That make it lean and make it store less information, right? And then the last thing, which I also hinted in the producer side when I was explaining, that producer basically batch the messages before sending it. It do not send each message instantaneously. And that batching basically I mentioned in the sticky partitioning, where it's a linger MS and batch size. Right? So that basically helps you to batch the messages. So once you batch the messages, so what advantage the batching of messages provide is, instead of sending IP header, because when you are sending the message from producer to, let's say, broker, you will have to send in that IP packets, TCP connection with an IP packets. So instead of putting an IP header on each messages, now what you are doing, you are batching the message at one and sending the IP header only once. So these are the few optimization techniques that Kafka would have taken by default that make them much better than their counterparts, if you consider Kafka as a messaging queue, right? What are the things that, so these are some benchmarkings. So much faster in production of messages, much faster in consumption of messages, all those results from the previous slide that we just discussed, right? Batching of messages, stateless broker, operating system caching mechanism, horizontally scalable because they are work in a concept of partitions, right? So you can horizontally scale them. Data replication for fault tolerance, you can put different partition, different brokers, right? And you can host that like replica and leader in different regions so that you have a fault tolerance, right? So all those things are handled at Kafka layer. So now let's say we have understood the ingestion data pipeline. Now the second thing that we should be worried about is how do the data flows from the Kafka pipeline. So what format of data should be passing through the Kafka and what format of data should be consuming from Kafka. How to make that call basically. So there's a concept called encoding. So when you are working with memory, what happens is, when you're working with memory, you have your data is getting stored in like arrays, lists, things like that. Why? Because your CPU is very optimal to use that, right? It's optimized to use those things. So that's why they are stored in that way. But think about a problem. When you want to move the same data through, like, let's say through network, or you want to write the same data and send it through a file or things like that, right? Then you cannot use the same in-memory data structure to write those data, right? So what you will do, you will encode them in a stream of bytes instead of using an in-memory data structure. That encoding of in-memory data structure to stream of bytes is basically called as encoding. So there are different encoding mechanisms. We'll try to cover quickly each of them and understand what are pros and cons of each encoding mechanism, right? So we'll start with language-specific format. So every language, let's say Python, Java, everything has their own encoding mechanism. So let's say Python use pickle, Java use io.serializable. But the problem with that is that the decoding is also very coupled with the programming language, right? So now if you encode with the programming language, you have to decode with the same programming language. That's the problem. And also those are not designed with the efficiency, with keeping efficiency in mind, right? So we will move from more flexible, like basically that do not have any schema, to less flexible and more efficient. So we'll go in that direction to understand how it progressed going forward. So with JSON and CSVs, right? So JSON and CSVs do not have any schema, right? You can pass whatever you want. But still they are a de facto in the industry to share the data, either in JSON format or CSV format. Why? Because it's human readable. So that's why it is used, but it's not very efficient because you do not have a schema and you have to pass field name with all the fields, right? Then come Thrift and Protobuf. So Thrift was created by Facebook, Protobuf was created by Google, both are open sourced. They added a schema layer over the JSON body, right? So now instead of passing fields, you can pass the field tags. I'll show you in the example also. And then the Avro. Avro is much more performant. People mostly use Avro over Thrift and Protobuf. That also I'll explain why. So if you see this, right? Now let's say you have simple JSON, where you have a username, Martin, favorite number, something, and then like different activities that he might be doing, right? With JSON, if you'll see, each field is also encoded, like in a binary encoding. But if you see the Thrift binary protocol, the fields are not there. What we have there is field tags, right? So if you'll see, instead of username, we have field tags, 1, 2, 3, like that. So those are the optimization that it provided. So to make the body that we are sending more compact. So your Thrift and Protobuf are much more compact than what we can send in JSON, right? Then why did we needed Avro? What's the need of Avro in that case? So people were trying to use the same like Thrift and Protobuf while working with the Hadoop-like systems. But the problem with that is, if you think of a dynamic environment, right? What we need to we do not need to like compile a schema, get the generated code, use the generated code to again encrypt and decrypt the message. What we basically need, we just need to run a code which takes the data, encrypted data, and decode it. That's what we need, right? But all these guys like Thrift and Protobuf has the schema stored in ideal that you have to compile to get the generated code, and then use the generated code to encrypt and decrypt the data, right? What Avro solved is, you don't even provide the field tags. You just provide the schema with it, with the data. You just embed the schema with the data and provide it. But then the question might be, why JSON is not not a competitor to Avro, because that also has a schema in it, in a sense like you are encrypting fields there. Why the why Avro is not compared to JSON? Because you are also passing a schema there, and here you are encoding the fields. The reason is because we are using a Hadoop-like system, where you do not send each messages sequentially. What you do is, you batch messages. So when you batch messages, you can provide one schema that stands for that messages, and you are okay. You are still not sending schema for each messages. Also with the new creation of, like say, schema registries at Confluent, right? So instead of passing the schema, you can just use the schema ID, and like the consumer will automatically take it from there. Cool. So we have, now with this, we have discussed what format data should we be sending through Kafka, right? Now we'll understand what format of data should we be storing at our analytical workplace for efficient queries, right? Before that, I'm not sure if you are able to see the first image. What we are showing in that is, if you visualize a CSV, right, a row and column combination, you can store in the memory 3 ways. You can store row-wise, you can store column-wise, and you can store a hybrid of that, right? So when you store row-wise, it's much more efficient for your OLTP systems, because fetching a record, updating it quickly makes sense. When you store a data columnar-wise, right, your analytical gets happier, your analytical layer gets happier, because they need to do count star, things like that, right? So for that, those cases, they work on subset of columns, not on all the columns. So that's the reason your analytical workload gets more happier if you provide them the format of columnar storage. But if you think about, let's say, you can consider use case of AWS, you can apply the same use case to any other Google Cloud. Let's say you store a data in the S3, and then you query it with Athena, a data lake typical setup, right? In that, you also do select star sometimes. You just not always do select count, select things like that. You not always running analytical workload, but also do some select column names or select some certain rows. So other than analytical workload, you also need to think about the row creation. So the row creation also has to happen. So the hybrid approach is basically the best of both worlds. It takes the inspiration from row-wise as well as inspiration from column-wise, right? So what basically it creates row groups. And in each row group, it will create a subset of columns, right? So that's how it do. Now that's the structure of Parquet. So if you see, there's a row group. There are different row groups, row group 0 to row group n, and in each row group we have a chunk of columns. We do not have like whole column, we have chunk of column, and in each column we have a page data where actual data is stored, right? And that has a metadata of that chunk column. Also there's a footer, if you see at the end, right? Also there's a footer thing which holds the metadata for the particular row. So you have two things. You have metadata for column in the pages that are loaded, and the metadata of the row in the footer part. Right? We'll come why these are very helpful once you are optimizing a Parquet. So this is the example that will help you understand how the Parquet gets created, right? So let's say you have an uncompressed data, right? Then you do a dictionary compression where you assign like unique keys to each field, to each country, and then instead of mentioning those, you just mention the dictionary encoded keys of that, right? So let's say you assign 0 for United States, so you will mention 0 at the place of United States, right? And the second thing that happens is run length encoding and bit packing. So what happens in that is that they run length, so the 3 is consecutively happening 3 times. So instead of writing 3 times, you mention that over 3, 3. So that's how the Parquet gets created. This is the dictionary encoding of Parquet. There is another plain text encoding, but that's not very efficient. So let's discuss with the dictionary encoding only. So now with these, the 2 slides that we just discussed, right? The last 2 slides. These 2 slides will put a base for the optimization that we are going to apply, that we can plan to apply on the Parquet data. We should always compress the Parquet data. Why? So by default also they use snappy compression on the Parquet data. But if you, like we had done a benchmark on 10 GB of data, without compressed with snappy. The without compressed data was taking like 15 seconds, compressed snappy was taking like 5 seconds, so 3x difference. We should always think of partitioning. So you should not scan the whole data that's available. You partition the data, so you always scan a limited amount of data. But that second problem can also solution of second problem can lead to a third problem, where you end up in creating very small files, right? Now if you think, let's say data lake system, right, where Athena is there, S3 is there. Now you have very small file sizes, right? So you'll start picking small file size to even give you like a count of, let's say, number of rows for last 1 month, because there are so many small files are getting created. That also we should not create, right? Because we have also done a benchmarking of 16 files storing the same amount of data in 16 files versus 1024 files, and like it was 2 times different, 2 times much slower in a large number of files versus a small number of small files, right? So how to solve that? We have to manually repartition it. This also a use case for a lake house, right? Once I explain the last point, and I'll come why is the use case of the lake house. So with this, we can also do predicate push down. So let's say you have a query, select star from table where x is greater than 5. Now in the previous slide, we have discussed that there's a footer for each row group, right? So there the footer, in that has a metadata, which what is min, what is max for that particular row group. So when you are doing that, you can skip the row group too, because your x is greater than 5 cannot like come into that. So those are the optimization that you can do with Parquet. How the third point basically leads to one of the use cases, not completely, but one of the use cases for Lakehouse is they like either use Apache Hudi or either use Databricks, things like that, right? So all of them provide a default key by which you can like merge these files in a fixed size instead of having a smaller files. We'll quickly, like the last 2 points we'll quickly discuss. So we have, till now we have understood the ingestion pipeline. The second part we have understood is about the encoding and those things about that, right? And then we have also understood Parquet optimization. The third point is, now it's coming to the use case, right? How can we use the data? So one of the use cases, we want to set up MLOps pipelines with that, right? So let's take a sit back and think what are the problems in ML engineer lives are, right? So the first problem is someone is developing computer vision model, someone is developing NLP model, and you want to provide a uniform platform to all your data scientists, right? And all data scientists are not just running a simple jobs, they are running a very compute intensive jobs, right? The third is, people will say that it was working on my system, but not working on your system, right? So dependency management is a problem. Version control, you have to version not just the code part, but also the data and the model part. So if I say that all these problems that we just discussed in the last slide has been solved by one platform, which is Metaflow, right? So all these problems, right? So a different use case, you have an integrated environment that you can quickly move to cloud. For compute intensive algorithms, you can just use a decorator. It's a very unique thing. You don't have to even change your code. Just use a decorator, specify the resources, CPU and whatever memory or whatever GPU might need. So that's vertical scaling. You can also use for each for horizontal scaling. So let's say you have different learning parameters you want to try that with. So you can use for each and try different learning parameters horizontally. It gives you a local system feel, right? So with the S3 decorator, they have created a customized S3 decorator. This was developed at Netflix, so very much in close with AWS systems. So they have a S3 decorator which provide you a speed of what speed we get on your local system. It's like 10 Gbps type of speed for your data loading as well as your model loading. For dependency management, they provide a Conda and PyPI decorator which you can use to used for one particular step or for like complete functions. So they go to that level of granularity. One line of deployment to production and bringing that code to our local system for debugging on the same data set, right? Last topic. So we'll discuss so we have discussed the MLOps pipeline that we can set with this data set. The last topic that we'll discuss is your analytical workload. Now this is very important, right? Because most of our work, like as a data engineer, we have to maintain MLOps pipeline, but we are mostly also responsible for the dashboards that are getting updated on a real-time basis, things like that, right? So Superset was built at Airbnb, keeping 3 things in mind. They wanted to build a scalable, customizable, and a user-friendly BI tool. So they have tens or thousands of users running tens of thousands of queries each, right? With a very user-friendly environment. Components are simply, we can just move ahead, but it's like just, they have a SQL lab where you can run your, like very strong, very powerful SQL lab, you can run your SQL queries, you can have a data set concepts there as well. All the data connectors, you can implement caching layer for each chart, each dashboard, each data set by using Memcache, Redis, things like that. They also provide a row-based access control. This is the last topic that I wanted to touch upon is about the entity data modeling. Right? So I think most of us here would have already heard about dimensional modeling, right? Where we have fact table, dimension table, things like that. But with the cheap cost of storage and cheap cost of compute, right? Which is currently now in our life that's happening, right? We should not think about like having these fact tables and dimension tables separately. What we should think about is, let's say, if any use case that you can think of in your mind. Mostly, let's say, you might have a use case where you want to predict user churn, why the particular user has churned, right? So for that use case, always a use case comes with an entity in mind. So I want to find why the particular user has churned. So user is an entity here, right? So that's what happens. So if you think of so if I take the point from dimensional modeling to entity-centric modeling, what we are basically doing there is, we are moving the metrics that are there into dimensions, right? So if Kimball would have been here, he would be very upset, but that's what we have been trying to do here. So with that, what we are creating at the end is we are creating a very wide table, right? Why white table is white table do not cost us that much? Because we have Parquet optimization that we have just discussed. We also have a very low cost storage in terms of S3 and other cloud storage, right? So we can have a very wide table. We can use Parquet and things like that, optimization and things like that, and we provide a very thin semantic layer on the BI tool, right? So instead of handling the semantic layer at the BI tool, which is the case with Looker and things like that, where they have Looker ML and things like that, right? Instead of that, what we do, we take the semantic layer at the T part of ELT, right? So instead of moving that to a BI layer, we'll do that at a T part of the ELT. So I'll just example on that. How do we do that? So let's say you have a user entity that you are trying to create, right? You should add, and let's say the churn example that you just discussed, that's what we want to solve with that. So with that, what columns you will create in that is for a user, you will also create, let's say, LTV value. You'll also create time dimension, let's say last 7-day visit, last 28-day visit, last 90-day visit, things like that. And on the other end, you should, like with our current data system, like even with S3 Athena system, you can have a JSON blob sitting in your table, which you can just query by using JSON extract or things like that, right? So you can have like last 5 purchases of the user, things like that. So a complete user entity is embodied in this particular entity, and always all entities are work in progress. It's not always like, so like you might have like 200 well-defined fields that you would have created for a user, but still it is work in progress. You might like tomorrow get more fields to add to it, right? So yeah, so that's how you should build on a user-centric entity and add more columns depending upon the different matrices, like last 7-day visit, last 28-day visit, things like that. And also you should like bring the matrices, different matrices like LTV value and things like that in the user entity table. Just quick 2 mentions. We are not able to cover because time slot. Airflow and DBT, this also you should definitely give a try. Airflow is basically help you manage multiple data pipelines via UI, right? You can see what has failed, what has run, how much time does it took, retry from there, and then DBT, right? So DBT is a data build tool, right, which you can use to run SQL so that you can handle like you can run the SQL, you can trigger the SQL from there, and you can handle like your incremental loads and your like full refreshes from there. It's a very easy to use. So I'll definitely ask you to also go in deep about this Airflow and DBT. That's it. Thank you so much.